Okay, here I will talk again about the householder transformation. I wanted to make something more precise. Um, if you have a matrix bigger than a 2 by 2 matrix, if you apply your householder transformation, let's say you also already applied it to your first column vector, okay? What you have to be careful is once you've already if you've already applied the transformation to the first column vector, if you go to the second column vector, you only have to consider the submatrix. So if it's n by n matrix, if this is an n by n matrix, you only have to consider the n minus 1 by n minus 1 matrix, okay? So for example, if you do if you apply if you do a QR factorization with a 3 by 3 matrix, for your second householder transformation, you will only consider the submatrix of this 3 by 3 matrix, which will be a 2 by 2 matrix. Okay? And so you proceed as normally with this submatrix, but once you have found your second householder transformation, because you still want to multiply it with the original matrix, which is bigger than the householder matrix you found, which is only of the same size than this submatrix. So what you do is your second householder transformation will be equal to the ones in the 1 in the diagonal and 0 below and on the side, and here you will have your householder transformation if you consider only the submatrix. Okay, so this is for the second householder transformation. If you do it for the third, you will get a second one, then your householder transformation if you only consider the submatrix, basically, and so on. Okay, so you always get ones in the diagonals. So basically, what this does is allows the first columns of A that you have already reduced, basically, to remain unchanged. Okay, you can check that if you multiply it, the first column that have already been triangularized, they don't change anymore. I think I will do an example. Basically, let's say we have the following matrix. 1, 1, 1, 1, minus 1, 4, 4, minus 1, 4, minus 2, 2, 0. We want to do a QR factorization with this matrix, and we will use the householder transformation. Okay? So we will proceed as always. So we have our 3 column vectors. So our first vector v1. Here we won't already have unit vectors, so we will use the formula of householder transformation divided by v transpose v to get the unit vector. Okay, So our formula for V1 is our vector A1, which is 1, 1, 1, 1, minus the magnitude of the vector, which will give us 2. Okay, so square root of 1 squared plus 1 squared plus 1 squared plus 1 squared, so square root of 4, which is 2, times our unit vector E1, which is 1, 0, 0, 0, and this gives us minus 1, 1, 1, 1. Okay, so our first Hausdorff transformation will be the identity matrix minus 2 times a vector V1 times V1 transpose over V1 transpose V1. So remember, we don't get directly a unit vector, so we divide it by V transpose V. Okay, so if we compute that, we get H1 equals 1, 1, 1, 1. There's 0 everywhere else. Minus 2. If you compute that, arrange that a bit, you get the following. You can do it on your own. It's just rearranging and some computing and matrix multiplication, and you will get 1 over 2 basically everywhere. 1 over 2, 1 over 2, 1 over 2, 1 over 2, minus 1 over 2. Here you get a minus, here also. So it's just computing. You can do it on your own. It's just multiplication. Minus 1 over 2, 1 over 2, minus 1 over 2, 2, 1 over 2. Okay? So this is our first Hausdorff transformation. If we apply it to our original matrix, if we apply that, we will get the following matrix. Okay, so we have only one non-zero element in the first column vector of A. Now, we will apply what I said at the beginning of the video. So we will only consider the submatrix. So this submatrix here, okay? Because we want to find an upper triangle matrix, basically, and so here it will be in the form 0, x, x, 0, 0, x, 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 0, think. And so here we don't want to, even if here we already have a 0 in this position, this isn't necessarily the case. We want that the second column vector has only 2 elements that are necessarily zeros. Okay, so we won't consider the whole second column vector of A, so A2. We will only consider the vector in this submatrix. Okay. So our submatrix will be, let's call it that way, will be 0, 0, minus 5, 0, 4, 2. Okay. Now if we do again some computing, we find that V2 is equal to this second column vector, but again we only consider the submatrix, so it will be 0, 0, minus 5, minus the magnitude of that, so times the second unit vector, which to the minus 5, so it will be minus 5, 0, 0. So here we are in the our second unit vector E2 is in the second component of the original dimension. So at the first we had 4 dimensions, and our first unit vector it was this one. Okay. And here, because we take the submatrix, the first component is already our second unit vector E2. Do you see what I mean? Okay, you don't have to be troubled because there is the 5 here. Just don't be troubled, okay? I hope I don't disturb you too much. So you get this result here, okay? Yeah, and so we get that this is V2. We get that H2 is 1. Remember this 1 here. So the days are 1, 0 everywhere, and our second Hausdorff transformation of the submatrix. Okay. So this Hausdorff transformation of the submatrix, it will be 1, 1, 1 minus 1 over 25 times minus 5, 0, minus 5 times minus 5, 0, minus 5. This will give us 0, 0, minus 1, 0, 1, 0, minus 1, 0, 0. And so now we apply that result. We apply this how can I say that? We apply this result to our original matrix, and we go back in 4 dimensions. So we will just rewrite that. So yeah, I will just rewrite it in 4 dimensions. Okay, and so this is H2, and so we will apply it to the matrix we got after our first transformation. So we can just write H1A. Remember, that's the matrix we get after our first transformation H1. You can give it a name if you want. So this will be again this vector this transformation. It's a bit bad written, sorry. Times our matrix 2 0 0 0 3 0 0 minus 5 2 0 4 2. Okay, and so you will get that you will get the following result. You should get the following result. This matrix here, 0, 0, minus 2 4 0. Okay, so here by luck our last element here is already 0. Okay, otherwise you just consider again the sub matrix here. I think you could do it that way, and do again the Hausdorff transformation, and then you would get two ones here in the diagonal, so that the first two columns remain unchanged. And here you will put your transformation, so it's H3. Okay. And you will apply that to this matrix here. And so if this element here in that position wasn't already 0, okay, so I would do it that way. Okay, and it's in this way that you can triangularize matrix that are bigger than the 2 by 2 matrix, of which I did an example in one of my videos. Okay, and it's that way that I think that the computer does. Okay, and so you will get your you will get your QR decomposition, A equals QR. So Q transpose A equals to R. So we got our upper triangle matrix R, and all this Hausdorff transformation applied to A. So H1, H2. So here we only have 2 transformation because we don't need a third, but you could have a third H3, but here it's not the case. Applied to A equals to R. So we know that this here is equal to Q transpose. So you would find that Q equals H1 transpose H2 transpose. Okay. And so you can find the Q that way if you find the product of these two Hausdorff matrix transpose. Okay. And so you can find your QR factorization. Okay. So I hope I made it clear. Yeah. I hope this video was helpful. So yeah, just remember that if you have a matrix bigger than a 2 by 2 matrix, to find the successful Hausdorff transformation, you need to always consider the submatrix, the submatrix, and so on, and to put ones in the diagonal. And so you can do it that way to find your upper triangle matrix to do your QR decomposition. Okay, thanks for watching.